Speaker is David Polarski, who tells us about dark energy models.
Okay, so hello everybody. I don't belong to the happy few that Leszek mentioned yesterday that attended all the COSMO meeting, but I was at the 2015 meeting talking as a first speaker on Thursday after the banquet. So now I'm the third speaker, but still after the banquet. So maybe in 2021, I will be the second speaker after the banquet. So I have been spending now a couple of weeks here at Cassi, which is a few kilometers away, in a very, very lively environment, and I enjoyed very much as I like Korean food, which is a wonderful discovery for me. Okay, but my talk is on dark energy models, and so I will talk about the growth index. So many of you have heard about it. My talk will be also on mathematical beauty of the subject, but also you will have some information for those who are taking part in this impressive attempt of the community to get precise numbers on our universe. They will also get useful information here. So just to remind you, the framework, you know that matter perturbations, okay, matter perturbations can be characterized by the growth function, which obeys this function, okay? I will also consider modified gravity models. And as you know, a convenient parameterization is this one, okay? Now, we should remember that actually, S delta M is a function both of time and scale. The same will happen with gamma. This is the first lesson that you can just not escape, okay? So it's actually not a parameter, this gamma here, okay? But it's actually a function. But you can hope it's close to a parameter. Okay? And actually, as you know, in lambda CDM, gamma is very close to 0.55. And actually, not only in lambda CDM, but in most smooth models in general relativity. Okay? Okay. But it can be very different in modified gravity models. Here, I should mention that the work I will present, for the results, most of the results I will present were obtained with my colleagues and friends Starobinski and Giacomini. I should also say that this parameterization actually goes back, which is actually very nice. I mean, there is a lot to dig there. Came from Peebles in 1984, who wanted to characterize the growth of perturbations in an open universe. And then little by little, it was revived lately in the context of dark energy models. Okay, so a first thing to realize is the following. If we look at the slope of gamma, so the prime here denotes a derivative with respect to redshift. If I look at the slope today, 0, okay, versus the value of gamma today, well, you see that you get straight lines, and here I've depicted, I show several dark energy models. First, I fixed omega m naught, but I vary WDE naught from top to bottom. So this is minus 1.4, minus 1.2, and so, and this is lambda CDM, by the way. This is minus 1, okay? And this plot is just to show that if you fix omega m naught and you fix WDE naught, and you put it in this equation here, this equation, okay, then you have a, yeah. Yes. Right. Okay. Last one. Okay. But for the slides, I use this. Great. So now my both hands are And I have this. Okay, wonderful. Yeah, this is much better. I gave it to too many people when I was in Rome. So now, okay. So here, again, so you see you have this relation, okay? And this is just when you plug into the equation those two values. You see that there is a constraint between both, but what is the real point? The real point is that there is only one value of gamma naught, okay? For each line, there is only one value of gamma naught that will give you a perfect, well, at least derivative constant at 0, okay? If you want gamma to be constant, it should at least have a 0 derivative today, okay? It's not guaranteed that it will be in the past, but at least today, okay? And you see, this very simple plot just shows you that to have a constant gamma is very peculiar. You must be exactly on these values on your line. Okay, now I use this one. Okay, so now I will show you a few exact results inside GR, okay, when gamma is constant. And by exact, I mean that they are really exact when gamma is constant. No approximation. This is what I mean here by exact. Okay, the first thing is that all background quantities will be given in parametric form. Okay, so I can express A in function of omega m, T in function of omega m, okay, all of them. In particular, I have here this equation, which gives you the equation of state of dark energy as a function of omega m. Okay, let's see now what this equation tells us. First, in the asymptotic future, when omega m goes to 0, we have this expression, okay? Which means that if we want an accelerating universe in the future, we need gamma to be in this range. In the asymptotic past, which is omega m going to 1, so you see my notation in the future, plus infinity, in the past, minus infinity, because I think in log A, okay? You have this expression. So this is a bit subtle, but not too difficult, because you see this goes to 0, this goes to 0, but it's easy to get the formula, this formula, and you see that gamma is between 0.5 and 0.6. Okay. When it's 0.5, you see immediately I avoid it because it's singular. And when it's 0.6, I have exactly 0 in the past. So if I want dark energy, it should be a bit below, okay? Okay, so the bottom line of this is that gamma should be here in this range. Okay, so this is something I'm using that shows you, okay, it gives you a feeling of the expression that I gave you of WD as a function of omega m. Because here I show you W as a function of gamma for fixed omega m. Okay? And I take omega m today, omega m naught. So this gives you the possible values of W today as a function of gamma. And you see that actually, if you want a W today, because if I fixed omega m naught, per definition, I get W today. So if I want W naught to be between minus 1.2 and minus 0.8, which covers, I believe everybody will agree, most of at 2 sigma, what we expect, then gamma will be between these values. And you see the 0.55 is not is in this, actually it is 0.555, it's there. Okay? So this is just because I have to cut between here, and you see this is the range, and this is this. Okay? So this is what we expect, because actually, in the past, the gamma was close to gamma, as I will show a bit later. But these are exact results. This is when gamma is strictly constant. Okay, what are further consequences? Further consequences are that if gamma is between 0.5 and 6/11, then in the past, we have phantom dark energy. And by phantom, I mean just W smaller than -1. Okay? If gamma is between 0.5 and 2/3, then W in the future is of phantom type. But you see, this covers this. In other words, deep in the dark energy dominated era, phantom regime is unavoidable. Okay? There is no way to escape it. And this is important because this means, for example, that quintessence cannot have a constant gamma. Okay? Because even if it fits the past, it will not fit the future. Because at some stage, it will turn phantom. And actually, this was the result that Alexei Starobinsky showed in a workshop, I think it was 7 years ago in Montpellier. And I was very intrigued by this, and this brought me later to work on this aspect of the problem. So let me remind you a few things, because these are exact statements, okay, and not, I would not say sloppy statements, but approximate statements, okay? When gamma is 0.6, strictly 0.6, okay, then W in the past is 0. When gamma is 6/11, the famous 6/11, then W in the past is -1. So this is the true mathematical definition of this 6/11. Okay? When gamma is 6/11 and you take a constant gamma, then W in the past is -1. And remember, when gamma is 2/3, then at infinity, in the future, it's -1. So this is why it should be higher than 2/3 to be higher than -1. Okay. So, as I just said, it cannot be realized by quintessence. But actually, there is something interesting here. There is a way, mathematically, to have quintessence having a constant gamma. It's namely to have tracking dark energy in the past. Okay? If I have tracking dark energy in the past, I can escape the no-go theorem that I mentioned. And the reason is very easy to understand. First, I explain the physics. All the relations I've deduced take into account that I go back to omega m equal 1. Okay? Which means that omega dark energy goes to 0. But actually, if I have tracking dark energy, at a certain stage, omega m will get stuck to some value, and omega d also. Of course, the sum is 1. Okay? This is just when, in the past, the W of dark energy goes to 0. And you can very easily see it in this plot. Okay? Here I give you an example of a W for constant gamma, which is higher than 0.6. And you see, okay, I come closer to the screen. Okay? I do it with my hands. If I raise gamma, the curve will go like that. If I lower, it will go like that. If I take 0.6, it will end exactly here. Okay? This was the result that I mentioned. So, in other words, we have an infinite number of roots, okay, for omega m at minus infinity equal 1. And by minus infinity, I mean this, of course. Huh? It is the limit in the past, okay, for gamma between 0.6 and 1. So this is a very nice result, okay? Okay, now, let's see if really we can have a quintessence in this way. Well, actually, mathematically, yes, but physically, this is my point. Can we have it physically? Does it fit our universe? Okay. What are particular cases? So now I consider values of gamma between 0.6 and 1. So let's take a value that is very close to 0.6. Okay, from observations, we know that epsilon is smaller than 1%. Epsilon is the difference between 1 and the value of gamma in the past, okay? This is much smaller than 1. Actually, epsilon is just omega, what we often call in the literature omega early dark energy, okay, in the past. And we know it's smaller than 1%. Okay, this is okay. However, W infinity is smaller than minus 1, because you see, I'm higher than 0.6. Okay? A bit higher than 0.6. Not enough. You remember? I have to go higher than 2/3 to avoid phantom in the future. So this is certainly not enough. No, let us consider the following cases. In the following cases, I avoid this, because you see, here I'm just on the edge. I'm just on the edge, and here I avoid it. Okay? There is no phantom dark energy in the future. However, you see that the price to pay is that omega minus infinity is much too small. Actually, it's very simple to understand here from this curve. Okay? If I raise the gamma, you see that the omega m minus infinity gets too small. So finally, what we can say is that constant gamma is ruled out for quintessence, and it is also ruled out for constant W dark energy. Okay. Now, is it nevertheless possible to get a constant W dark energy? It is possible beyond GR. Okay? If I write my equation, okay, and I assume WDE is constant during all the expansion, I get this expression. And I can try something a bit weaker, which is to say the WDE is constant during part of the expansion. And typically, I take the past of our universe until today. And then I get this expression. But you see, this will be strongly violated in many modified gravity models. Why? Because you look at what happens today, okay? If you look at what happens today, you see that actually this will be much less than 1. Okay? And now, let me show you two models, okay? A scalar tensor model, okay? Okay. This is here G effective. This is the expression. This is the omega Bronsdicke parameter. The omega Bronsdicke parameter today is very large. This comes from solar system constraints. So this term disappears. In other words, G effective today is very close to this, and G effective today is by definition G. So in other words, G naught is 1. And so the condition that I mentioned on the previous slide cannot be realized in no way by such a theory. Another interesting point, another interesting model, sorry, is the FR model. And please note that I show you here two models which survive the major discovery that came with the speed of gravitational waves. Okay, these models survive. They are not ruled out. Okay, let's see. For FR model, G effective over G depends on Z and K. Okay, it has this expression, but actually, due to these conditions, you see that G, this here, in other words, this expression is always bigger than 1. Whatever scale, whatever time, it's always bigger than 1. So again, this explains why it cannot have a constant gamma. Okay, now I would like to come back to GR. I want to come back to GR. Okay, this is my equation for gamma. It's a first order, highly nonlinear equation, as you see. And I write it in a convenient way. Actually, here there are derivatives of omega m, but they actually give WDE, okay? And if I take WDE constant, then this becomes a simple equation. And here are the plots. So, these are for, I think, minus 1.2, minus, I think this should be minus 1 here. This is lambda CDM, okay? And this is, I think, minus 1.8, minus 1/3, and this is approximately 0. Okay. What do you see here? First, we live here. We live here. So, in a bit provocative way, I could say that we happen to live at exactly the time where gamma starts being non-constant, highly non-constant. But you see, it's not exactly constant. There is still a small change, but you see that it's quasi-constant, okay, until today. It's quasi-constant. There is a big, I should actually take this curve, okay, lambda CDM, okay? You see there is a small increase. Okay, but the interesting thing is that in the past, you see that gamma is constant. If gamma is constant in the past, I can use my equations that I showed, my exact equations, and I can give the initial condition for gamma. So the bottom line here is that I can use this exact equation, use this exact initial condition, and integrate to get gamma in the future. Okay? Now, if I do my calculations, I see that gamma as a function of omega m, is given by this expression, okay? I think this never appeared in the literature. This appeared in the literature, but I vaguely remember there was a typo, a power missing, something, in an old paper in the 90s by Wang and Steinert, I think. Okay? It's remarkably accurate. You don't, okay, this is for the sake of beauty, the second term. Actually, this is already below the percent level until today. As I told you, it's really remarkably quasi-constant because I go from the infinity past to today and I get an error of less than 1%, a precision, an accuracy of less than 1%. But of course, when you make assessment of dark energy models, you want gamma as a function of Z around gamma naught. But then you have to calculate gamma naught numerically. You have to do it using these initial conditions. You plug here gamma naught. You obtain, sorry, numerically gamma naught. You plug it here, okay? And then you expand, okay? Gamma prime naught is given by my equation. It's no more free, okay? And again, the accuracy is below the percent level up to Z of order 3. So, I would say, when people work with the growth index in lambda CDM, they should not forget that it's not exactly constant, okay? When you will make when redshift space distortion measurement and other measurements will narrow the errors and they will become really on the percent level, you should not take gamma constant, okay? Because you introduce already at the beginning an error. Okay, another interesting problem is the future, because you remember, I showed you, you see, you might think that this is some numerical artifact. Not at all. Not at all. You can show that this diverges in the future. Okay? And this diverges too. But this does not diverge, because omega in the future should be finite. And actually, I was very happy to find this, because I had this equation with a term here. And if it would diverge, it would be bad. So, but this diverge, okay? This diverge. And this is exactly here. If you try to do it numerically, your computer will start shouting here, because it cannot follow. Okay. In the asymptotic past, we have this formula. We recover the gamma minus infinity. Here, there is a subtlety that I will skip now. I want just, with a few minutes left, show the following. If I use this equation, and I assume this behavior, so this is not really a parameterization. I assume this behavior, and I will restrict myself on small z intervals. Okay? Then this is a genuine Taylor expansion. Okay? So what I do is very nice. I assume this, and I use supernovae on small redshifts. Then I can just, for each couple gamma naught, gamma 1, I can reconstruct the background using this equation, and by reconstructing the background, I can fit with supernovae. And this gives me a confidence regions for gamma 1, gamma naught. Of course, we expect it to be very broad, and you see this is exactly what happened. However, the interesting thing is here the lower bound. You see, you can say that inside GR, gamma naught can never be smaller than 0.53, and gamma 1 can never be smaller than minus 0.15. Okay? It doesn't mean that if you are above, you are necessarily in GR, but it means that if you are below, you are not in GR. Here, this is the, okay, I skip it. Now, a very last thing that I want to show. I think I have 2 minutes. Yeah, okay. So, here, actually what we do is that we want to see what are the modified gravity models that could mimic lambda CDM. So, I take a background. I take a background which is lambda CDM. And this information is stored here. Okay? I take a gamma which is of this kind, and this will be stored here. Okay, and of course here. And then I reconstruct G, because it becomes an algebraic equation. I reconstruct G at low redshift. And you see here a few examples. I go around lambda CDM, so gamma naught is 0.555. I go around lambda CDM, so I go around gamma 1 is minus 0.017. And by the way, gamma 1 is gamma prime naught. It's just another name. And you see that we have this region, okay? Which means that, what does it mean? So here is gamma prime naught, gamma 1. Here is gamma naught. This point is lambda CDM. And I build all the G, I reconstruct all the G around this point, okay? And I look at their behavior until Z of order 0.3. Why? Because then I can trust my expansion. And I see that in all this region, GZ is smaller than 1. In all this region, GZ is smaller, bigger than 1, larger than 1. And this starts belonging to it starts belonging to this region, but it will shift. So all the reconstructed modified gravity models here start with a G effective. No, they start with a G effective smaller than 1, but they will join this. So it belongs to this here. They start below and they go like that. Okay? All the models here, they start initially at larger values than 1, and they finally go down and they do this. Okay? And when I move in this direction, actually I don't cross G. Either I do this, I do this. So actually what I would say is that this makes, okay, we play here a game. We want to mimic dark energy. We want to mimic, lambda CDM, both at the background level and at the perturbation level. And you see that the price is very, very high. Okay? Actually, you need to cross G at very low redshift. The G effective should cross G at very low redshift. So I will finish with this slide, which is ongoing work. It will be finished soon. And the bottom line here is just to show that in this scalar tensor model that I showed, G effective, okay, for lambda CDM background can never decrease. Okay, it can never decrease. If you want something that decrease, you have to take a WDE bigger than -1. So this result will still hold for phantom dark energy. So all in all, okay, you know there was a big interest in explaining data by adopting modified gravity with a decreasing G effective. So the last slide shows that this is probably very, very uneasy to get. And anyway, it is probably not favored by supernovae data. Okay, I leave this conclusion here and I will finish here. Thank you for your attention.
Questions?
Yeah, just to make sure I understand the very last point. So, of course, supernova wouldn't give you gamma because they don't measure growth. But I think what you do here is to calculate, assuming GR, calculate gamma from omegas.
Yeah.
Right?
Yeah.
But
So
this is a bit misleading thing to say because supernovae never measure growth. They have nothing to do with density fluctuations.
no.
Right.
Supernovae, what they measure, of course, is the expansion, the Hubble.
Right.
Okay,
That's right.
and this is exactly what we do.
Yeah.
So in this sense, you're right,
Right.
but I'm right too.
So this is a prediction from supernova data, which should then be tested using fluctuations.
Yes.
That's what you're trying to say.
Yes.
Yeah.
What I'm saying is that if you assume GR and you take the supernovae data and you take the low Z supernovae data, they give you this constraint.
That's
Absolutely. You're right. Yeah.
Okay, thank you. Any other questions? Okay. Thanks.
Okay.